Chapter 1 Fundamentals of Thermodynamics, Section 1.7 Mixtures of Gases, Liquids, and Solids. First, let's look at a mixture of two ideal gases. For example, if we have two ideal gases A and B, or helium and argon, we can mix them. And then we can use the ideal gas equation. P sub A is equal to N sub A times RT over V. P sub A is the partial pressure of A, N sub A is the number of moles of A. We have the same equation for B. And then we can calculate the total pressure. P total is simply P sub A plus P sub B. Therefore, it's actually N sub total times RT over V. N sub total is the sum of N sub A and N sub B. Note that A and B share the same container, they have the same volume, and also they have the same temperature. Now we can look at the mole fraction of these two components. X of A is the mole fraction of A, it's simply N sub A over N total. X of B is N of B over N total. XA plus XB is equal to 1. What if you have three components, A, B, and C? Still, the sum of the three mole fractions should be 100%. Now let's look at the partial pressure again, and this time we'll relate the partial pressure to mole fraction. So the partial pressure of A divided by the total pressure, you can see it's N sub A RT over V divided by N sub total RT over V. RT over V cancel, and then we have N sub A over N total, we have the mole fraction of A. Similarly, the partial pressure of B over the total pressure is equal to the mole fraction of B. And therefore, we have these two equations. P sub A is simply X sub A times P total. P sub B is equal to X sub B times P total. P total is the sum of the partial pressures of A and B. Now let's look at a few numerical examples. 1.7.1. Calculate the partial pressures of nitrogen and oxygen in dry air at sea level. At sea level, the air pressure is 1 atm. For dry air, the mole fractions of nitrogen and oxygen is approximately 0.78 and 0.21. And therefore, the partial pressures are simply 0.78 atm and 0.21 atm at sea level. Example problem 1.7.2. Calculate the partial pressures of nitrogen and oxygen in dry air that's compressed to 2 bars. So once it's compressed to 2 bars, we have an increase of the partial pressure for both gases. And we can still calculate the partial pressure by using the total pressure multiplied by the mole fraction. The total pressure is 2 bars. The mole fraction of nitrogen is 0.78. After the multiplication, we get the partial pressure for nitrogen, which is 1.56 bars. Similarly, we can calculate the partial pressure for oxygen. Example problem 1.7.3. Calculate the partial pressures and mole fractions of N2O4 and NO2 at 100 degrees Celsius. Let's say the total pressure is 2.00 bars. The equilibrium constant for this reaction is 15. So we'll need to use this information. The equilibrium constant of pressures is 15, and we can set two variables. We say, well, the partial pressure of N2O4 is X bars. The partial pressure of NO2 is Y bars. Therefore, X plus Y is equal to 2. Now we know the equilibrium constant, 15. Therefore, Y squared over X is 15. The reason we need to square Y is because of the coefficient 2 over here. And we have two equations. We can solve these two equations because they contain only two variables. The solution is X is equal to 0.213, Y is simply 2 minus X, 1.787. And then we get the partial pressures for these two gases. Now, in general, for a mixture of many types ideal gases, for example, what if we have 100 different ideal gases? Then still the total pressure is the sum of partial pressures, and the partial pressure is the mole fraction times the total pressure. For species I, P sub I is simply X sub I times P total. And based on this equation, we can actually tell the sum of all mole fractions is 1. And also the sum of the number of moles of all species is N sub total. A gas mixture is always homogeneous. Well, we cannot say the same for liquids or solids. For example, if you mix water and oil, it's not homogeneous. If you mix gold and sand, it's not homogeneous. But sometimes we do have homogeneous solutions or even homogeneous alloy. For example, if we mix water and methanol, it's homogeneous. And if we actually melt sodium and potassium and then allow it cool down to be a solid again, this alloy is homogeneous. For homogeneous liquids and solid mixture, again, we can simply calculate their mole fractions by using the number of moles of sodium divided by the total number of moles, or we can use the number of water divided by the sum of water plus ethanol to get the mole fraction of each component. Now let's look at one example here. Example problem 1.7.4. Calculate the mole fraction of lauric acid and myristic acid in a mixture that contains 3 grams of La and 0.3 grams of Ma. I'm going to assume this is homogeneous mixture. You can actually heat up this mixture, 3 grams of La, 0.3 grams of Ma. You can melt them and then you can form a homogeneous liquid. Now let's do the calculation. What are the mole fractions? If you want to calculate the mole fractions, the first step is always to get the number of moles for each component. Over here we have 3 grams of La. We look up the molar mass of La, lauric acid, it's 200.3, and also we can just calculate the number of moles for Ma by looking up the molar mass of Ma. The calculation is straightforward. It's just mass over molar mass. We get the number of moles. Now the mole fraction of La is the number of moles of La divided by the total number of moles. We get 0.918. The number of moles, the mole fraction of Ma is simply 1 minus this because we have a 2-component system. Now finally, what are this lauric acid and myristic acid? Those are just long carbon chain carboxylic acids.